Alhamdulillah, thanks for Allah subhanahu wa ta'ala for all his blessings and bounties that he has bestowed upon us. فَبِأَيِّ آلَاءِ رَبِّكُمَا تُكَذِّبَانِ. Today is 26th of December, Saturday, in fact, and we are going to talk about perhaps pretty last lecture of this course. We'll try to wind up this particular course. We started off way back from the very basic things. We tried to scratch the surface, and also partway through the journey, we have tried our level best to polish those concepts which are essential at this level to somehow, to some extent, we could feel the difference between this level and the level that we already had and the previous years. Same thing is there, but how do you look into the extended version of those basic concepts? So today we are trying to wind this whole course by taking into consideration a few more applications of integration. If you remember from the last lecture, we discussed about the geometrical interpretation, how you come up with the idea of definite integral. So it is going to be the limiting case of the Riemann sum. Geometrically, we say that it is going to describe area under the curve between the boundary points, and those boundary points are basically the limiting values to the definite integral. So now we expedite this particular concept by taking into examples from the real world phenomena. Before we move on with the application, I have made a few, the annotated version is there. For example, over here in the very first case, rather than taking only points of interval from x0 to xk plus 1, I believe. So we go all the way from A to B by subdividing the complete length of interval into n rectangles. So the points would be x0, x1, x2 up to xn. Since for the very first case, if the function is increases, so if the function increases with respect to time, so then the altitude of each rectangle would be considered by looking into the length of its left edge. So for the very subinterval, the left edge would be corresponding to x0, and to the last rectangle, the left edge would be corresponding to xn minus 1. So annotate this one. Pretty much on the same line, when we talk about the decreasing behavior of the function, then the altitude of each rectangle would be considered by looking into the length of its right edge. So the first subinterval is basically from x0 to x1. Yep, from x0 to x1. So the very first rectangle. So the right edge is corresponding to x1. So this is how f of x1 is there. For the second one, the right edge is going to be corresponding to x2. So once you combine together the sum of all The areas, it is going to be the total area. So the very last one is going to be corresponding to the right edge of the last vertical strip. Corresponding to the vertical strip, there is going to be a rectangular portion. So this is all f of x and z. So small, you can say corrections are there or annotation is made in the text. We can figure out the corresponding geometry appropriately. Today, we are going to extend our journey to talk about few applications. One of the prominent applications of integration is to find arc lengths of plane curves. Curves are there, being a continuous function behind the scene, and we are interested to capture the length of that curve. How would you do that? There are formulas behind the scene based upon the nature of the curve. But over here, we are not going to go with the proof of those formulas. Rather, we will try to figure out the message behind the scene. Proof is there. I mean, because of the time, we are not going to go with the proof. Some of the details, the essential details are there to describe the whole procedure behind the scene, and we look into that. Before we move on, have a look at this expression. I believe that we already have gone through with the derivation of that one. So the derivation of this one is pretty much on the same basis as we have gone through with the derivation of this expression. If you remember the article curvature, I believe that before looking into the definition of curvature, we discussed some basic concepts over there, ds upon dx, an expression for that, an expression for ds upon dy, an expression for ds upon dt. Pretty much the same things are going to be utilized over here. Summarily, you closely resembled, we can look into the close resemblance of this thing derived over there and pretty much over here. All right, how you look into the lengths of plane curves, the arc lengths. We try to figure out this one. For example, behind the scene, we got a continuous curve, y is equal to f of x, described over the interval from a to b, should be a closed interval because the continuity is always discussed against a closed interval. And another way to describe this curve by representing it in the form of an arc. For example, it is going to be AB. I mean, for the sake of description, we say that it is going to be represented by the arc AB. Then what we do, we will subdivide this arc or the portion of the curve into small subarcs, into small subcurves. Finitely many numbers are there by means of the points P0 and P1, P2, P3, and the very last one is against the combination of Pn minus 1 and Pm. And then what we do, we will describe the sum of lengths of all the n chords corresponding to each arc, subarc, corresponding to each subcurve. There will be a chord, and we will look into the length of one chord. So pretty much the same idea that we described over there, the chord length. We know the difference between arc length and chord length. You need to go back to the article curvature. So over here, simple idea is we got a continuous curve. We will subdivide into small pieces. How those pieces are there, they've been basically described by means of the points. First pair, second pair, third pair, and then so on. So have a look. and the geometry, we need to go on the side of this board. All right, so we got a continuous portion of the curve, for example, described in the xy plane. For example, like this one. So described over the interval from A to B. The left extreme value of x, so you could label it like x naught is equal to A, and the right extreme value is going to be B for xn. So what we do? We got a curve y is equal to f of x. We subdivide into subarcs. How we do that? For example, we got a point P naught corresponding to x naught. Then we will be having another point over there, P1. What is P naught? Effectively, P naught is an ordered date corresponding to x naught. The value of the function would be f of x naught. And similarly, P1. So corresponding to x1, we will be having P1. So what we do? We basically look into this portion of the curve, that one, from P naught to P1. So this is going to be one of the piece. Once you subdivide into finitely many subintervals, and against each subinterval, we will form an arc. Piece of the arc is there because the complete arc is there from A to B. So that would be Pn. So what we do? We subdivide into small pieces over there. First piece of the curve is there. First piece of the arc is there. Corresponding to this arc, so that one is going to be a chord length. And if you remember from the previous lectures, while discussing curvature over there, we got very prominent result, very vital result, that the ratio between arc length to chord length, or the other way around, is unity, is always going to be 1. Once we talk about the limiting case, if you have infinitely many pieces over there, or when you say that those 2 points, like in this example, P naught and P1, they are very close to each other, just in the neighborhood of each other. We say that hardly any significant amount of the difference in terms of chord or the corresponding arc. If you take the friction, the ratio between them, the friction between arc length to chord length or chord length to arc length, it is pretty much the same thing as a limiting case. So this is it will result in the form of unit 1. So that's what we are doing. We subdivide the complete portion of the curve into small portions. So the first piece of the curve is there. By joining the points P naught and P1, so this is going to be arc, and here you go with the chord. We know the definition of chord. Difference from the secant line, I mean a line passing through 2 points of a curve is going to be a secant line. If you cut it down to those endpoints, I mean if the endpoints are striking the walls of the curve, it is going to be chord. So chord. So this length, this portion of the curve, is going to be measured by the length of the straight line. For the second one, second portion of the curve, we will be having this chord joining the points P1 and P2, and so on. So this one could be observed by that. For example, this is going to be the portion of the curve corresponding to the point Pn minus 1 and Pn. So against this portion of the curve, we will look into this chord, straight line joining the points Pn minus 1 to Pn. And then pretty much on the same line as we have described the concept of definite integral by subdividing the interval into finitely many subintervals. So if you combine together the sum of those corresponding rectangles, this is known as Riemann sum. And as a limiting case, we say that it will be exactly the same as you capture the value of definite integral. All right, so following this figure, we look into the description. We see that let the graph of a continuous curve be there defined over the interval from A to B, represented by the arc AB, for example, initially. Then we subdivide into small pieces, finitely many small arcs by means of the points. So the very first arc against these 2 points, P0, P1, the second one, third one, and then so on. Let us denote the sum of the lengths of those n chords, because against every arc there will be a chord. So how do you measure this one? It is basically a straight line. Look into the length of the straight line. So we combine together, and the sum of lengths of all the n chords is going to be denoted by capital S. And then we bring into the concept of limit. Then the length of the arc AB is defined as the limit of S when the number of points of subdivision of the arc tends to infinity. We say that what is n? N approaches to infinity. There are too many, and the lengths of the chords approach to 0. There is hardly any significant amount of distance to be traveled from P, for example, P0 to P1, then P1 to P2, and then so on. So if they are closely, placed very close to each other, just in the neighborhood of each other, so we say that there is hardly any significant amount of difference between the arc and the corresponding chord. And this is all. We are computing the length of chords, but eventually it will take us to the length of those finitely many arcs, and eventually the complete portion of the curve. That's what is the message behind the scene. So what are the formulas behind the scene? Basically, we look into that. Depends upon the nature of a curve. We got 3 different cases, 3 different possibilities over there. For example, number 1 is that if the curve is described in rectangular coordinate system in terms of y and x, so then we know that ds upon dx, we know the rate of change of s with respect to x is going to based upon the rate of change of y with respect to x. What is this? Is the length sum, or in other words, is the length of the corresponding arc, is the length of the corresponding portion of the curve. So how do you get down with s? integrating both sides. That's the rate of change of s with respect to x. So taking integral on both sides, so we will be having this formula. So this is the formula. For finding the length of a curve, when the curve is given in a rectangular coordinate system, like y as a function of x. Other way around, when in the same coordinate system, x is given as a function of y, we have this formula ds upon dy. From here, just integrating again now with respect to y. So this is all the formula is it. So it's a matter of integration again. This is going to be integrand. It has to be integrated with respect to y. And third possibility is that when the equation of the curve is given in parametric form, in terms of parameter x as a function of t, y as another function of t, it should have been different one. I believe that. Okay, make a correction. I mean, that's a typographical error. If x is equal to f of t, y should be different from that. So make it like g of t, for example. So x as a function of t, y as a function of t, then we know the formula for ds upon dt. It's dx upon dt square plus dy upon dt square whole raised to power 1 by 2. Under that radical sign, we have got this expression. Integrating now with respect to t. So this is all the formula is it. So all you need to look into the implementation of these formulas corresponding to different nature of the curve. Y as a function of x, calculate dy upon dx, and then look into this expression to be integrated with respect to x. X as a function of y. Get down with the rate of change of x with respect to y, calculate this expression, this whole thing, and then integrate the resultant expression with respect to y. Of course, the limits of integration will be provided to you. And in the case of curve expressed in terms of parameters, x as a function of t, y, for example, g of t. So this is going to be the formula. Rate of change of x with respect to t, rate of change of y with respect to t. So this is how you need to integrate this expression with respect to t. Take an example. Find the length of the following curve. X is a function of t, y is another function of t, but different from x. So this is how you need to label that one as g of t. And the interval of integration is a from -2 by 3 to 1. So x is given as a function of t, y is a function of t, so we need to look into this formula number 3. That one. Against the curve, x is a function of t, y is as a function of t. So look into the rate of change of x with respect to t, the rate of change of y with respect to t, plug in all these values, integrate this one with respect to t over the provided limits from -2 by 3 to 1. So here you go. Interval of integration -2 by 3 to 1. Dx upon dt, dy upon dt, just calculate them from here. So simple expression is there. So the rest of the part is just a matter of integration. Once you get down with the appropriate formula, the rest of the part is just the matter of simple integration. Pretty much on the same line, we can look into the other examples. X is a function of t, y is another function of t. X is a function of y, so you need to apply second formula in this case. Fundamental theorem of calculus. Pretty basic, pretty powerful result is here. And we know that what is theorem? The most significant result, the most powerful, the most valuable. So we say that it is going to be not only powerful, but on top of that, it is fundamental. So if f is continuous on the closed interval, then capital F, described as integral of f of t, remember t is going to be dummy variable. Eventually, it will result as a function of t because the upper limit is a variable. A is constant, but the x is going to be a variable. So once you integrate this one with respect to t and then apply upper and lower limits over there, the result would be in terms of x. So this is all. It is going to be f of x. We say that f, capital F, being an integral to small f, is continuous on the closed interval AB and differentiable over the open interval AB, all sort of values, real values in between A and B, excluding the boundary points. This is how we describe an open interval. And its derivative is going to be f of x. That is, how you describe this one? For example, f, capital F of x is equal to this one. Then if you take derivative to the left-hand side, to the right-hand side, so differentiate the left and the right-hand sides with respect to x, for example, then the resultant is going to be small f of x. So f prime of x is equal to so take the derivative with respect to x, derivative to this integral will result in the form of small f of x. What the message is there basically? If you recall the basic concepts about differentiation and know the concepts of integration, we say that integration is the reverse process of differentiation. If integration is a reverse process to differentiation, so surely they are going to kill each other's effect. You got a function at your disposal, make a change in it by looking into differentiation, and then on top of that, if you integrate this one, you should get the original function back. That's what is the message behind the scene. From original function to differentiation and then integration. So this is the fundamental theorem of calculus. What is calculus? It's all about the rate of change. The rate of change takes us to derivative, differentiation being the process, and then the reverse process being integration. So this is how we all talk about rate of change everywhere. So what we observe from here, they are going to kill each other effect, derivative and integral. They will kill each other and we're left with the original function. And since in this case, we have the upper limit as a variable, so it will result in the form of a function of x. As a remark, continuity is discussed always against a closed interval, whereas differentiability is always discussed against an open interval. What is an argument? Why do you take open interval? Because the derivative does not exist at endpoints. Since there is no derivative, because in order to have derivative, you need to go back to follow the concept of limit, and we say that if the limit exists, it should be unique, whether it is calculated from the left-hand side or from the right-hand side. And since we are talking about the endpoint, whether it is left or right, there won't be the other side limit. So this is how we will not be having the other side derivative. And eventually we say that there won't be derivative at the endpoints. So this is how we have to exclude the endpoints when we talk about differentiability. But yes, for continuity, it is going to be, generally it is going to be against a closed interval, unless the endpoints are going to be like infinity. By default, they are not going to be considered as real finite values. Otherwise, it is going to be closed interval. So this definition has to be implemented, like in this example. What we see in this case, x is given as an integral. What we look into these examples, x is a function of y, and then we look into the formula, appropriate formula. For example, x is a function of y. This is the formula that we need to utilize. We will look into the rate of change of x with respect to that independent variable, and then that integrand will be considered with respect to y over the interval of integration by utilizing this variable of integration. But over here, what we see, x is going to be described as an integral. So what we do from here, by utilizing this fundamental theorem of calculus, f prime of x would be f of x by taking the derivative to this integral. So remember, it all based upon the limit. Upper limit is variable x, so result will definitely be in terms of x, f of x. So over here we see that the upper limit is y, so this whole thing will result in the form of function of y. So if you differentiate both sides with respect to y, so eventually it is going to be that expression, f of y. Now you have dx upon dy, that's what we were looking for. So limits are there from minus pi by 4 to pi by 4. So dx upon dy, plug in over here and then simplify this one. It's a matter of integration. Eventually it is going to be 2. Take a few examples from this exercise. Exercise number 6.3. Find the lengths of the curves. If we magnify, for example, this one. Find the lengths of the curves in exercises from 1 to 12. If you have a grapher, you may want to graph these curves to see what they look like. I mean, it's an additional component as an optional one. So sometimes graph is not going to be pretty easy, although we got an idea about curve sketching, but behind the scene, it's very demanding. To get the most appropriate graph, we have discussed those elements. 6 of the basic elements are there. Remember the word ISOAPR. Intercepts, symmetry, nature of origin, asymptotes, point of inflection, and then the region. So these are the elements you need to take care of. So once you care about those elements, only then you can look into the most appropriate graph. So anyway, it's an optional component. What we do, we will try to figure out these things. In all these examples from 1 to 12, we will try to figure out the length of the corresponding portion of the graph. Y is going to be described against the interval from 0 to 3. So it's a matter of curve. What nature of the curve is there? So we see that y is a function of x. Utilize formula number 1. Y is a function of x. X is a function of y. X is a function of y. So all the way down to example number 12. Example number 11 and 12. We need to bring in the definition of fundamental theorem. We have discussed this example, I believe that one. Utilize the definition of fundamental theorem of calculus, and then on top of that, see the nature of the curve to utilize one of the formula. So I would ask you people to look into those examples, 12 examples from this exercise for practice purposes. Now we move on to another prominent applications. Volumes of solids of revolution. How do you capture the volume now? Before we move on, keep an eye on the definition, or keep an eye on the difference between area and volume. Area is always calculated against two-dimensional object. And if you add one more dimension, means 3 dimensions are there. So volume is calculated against an object described in three-dimensional space. We already got an idea about the area of a curve described by definite integral. So again, we are looking for the applications of integration, but now in the form of volume now. Volumes of solids of revolution. Before we move on, we define solid of revolution. We say that the solid generated by rotating a plane region about an axis in its plane is known as solid of revolution. We know that two-dimensional object is going to be described in two-dimensional space. What is two-dimensional space? It is going to be a plane. So we will take as granted an object described in a plane, and we will rotate it about an axis. So we have two options, either x-axis or y-axis. So by taking an object described in two-dimensional space means plane, we will rotate it about an axis, either x-axis or y-axis. The solid generated by revolving that will take us to solid of revolution. How do you observe the volume of that solid? The volume of a solid of non-integrable cross-section area from A to B is the integral of AX from A to B. So eventually it will take us to this formula. We will talk about this formula because there are more than one versions. So that cross-section area is going to be integrated once you make a rotation about one particular axis. So it will take us to volume. To calculate the volume of a solid, we need to care about the following steps. Number one, sketch the solid and a typical cross section. I mean, the solid over there, the shaded region, normally we describe it. Find a formula for the area of a typical cross section. Find the limits of integration and then integrate it. Sketch the graph. Look into the most appropriate formula. Find the limits of integration, and then the rest of the process is a matter of integration. So these are the essential steps that we need to care about. So very first thing, volume modeled by disk. Disk method is there. The volume V of solid generated by revolving about x-axis, for example, we take into consideration the region between the x-axis. So again, the volume V of solid generated by revolving about x-axis, the region between the x-axis and the graph of the corresponding continuous function, for example, y is equal to capital R of x over the interval from A to B is given by this one. V is equal to an integral, definite integral from A to B, pi R of x k dx. So if you closely look into this one, so capital R is going to describe the radius basically of the corresponding circular object. And what if you combine pi together with the radius squared? So pi R square, we know that this is basically the formula to describe the area of a circle. Area of a circle is going to be described by pi R square. It all based upon the radius. It is going to be unique or fixed length of those infinitely many points from the central point R, radius of a circle. So pi R square is going to be area. And area is going to be two-dimensional object. So on top of that, if you add one more dimension, it will take you to the volume. So that's what we are going to describe. So the first one is there. When y is going to be a function of x, x-axis are involved, and the limits are there with respect to x from a to b, and we are going to describe it. So what we do, we will subdivide the region, for example, bounded by y is equal to f of x, into n vertical strips. So, and then we will consider only one disk, for example, with radius yk, height delta xk. The volume would be described by this one. I mean, keep an eye on again. If there is a disk means solid thing. Circular object is there, but it is going to be solid. There is no gap in between them. So we will be having yk being the radius of that one. So, or r of x, yk is equal to r of x. So then pi r square being the radius times one more dimension. What is this dimension? Height. So it will describe volume of one disk, and then we move forward. So keep an eye on the geometry. We have to go on the sideways board. So the first case is there, first possibility is that y is a function of x. Again in the xy plane, we got a nice curve, for example, that one, portion of the graph, y is equal to f of x, described over the interval from a to b, means the left hand point is a, the right hand point is going to be b, xn is equal to b, for example, that one is going to be x1. We subdivide into finite number of vertical strips. For example, the kth vertical strip is going to be that one. The corresponding kth vertical strip is this one. What we do, we rotate this one about x-axis. This thing is going to be rotated about x-axis. We take one of the vertical strip, just like, for example, this marker is there, it's a vertical strip, just imagine, and we rotate it about x-axis. So the rotation is made about the x-axis, and always positive direction is going to be the anti-clockwise. So for example, this is going to be one of the piece, and that one is going to be rotated about the line x-axis. So x-axis is there, we take one vertical strip. It's a two-dimensional object. Remember this whole thing. Y is equal to f of x bounded by a from the left, from the right hand side, by b. These are the limits. The boundaries are there. So this whole region is there, described in two-dimensional space, means in a plane. We subdivide this whole region, this total area, into finally many vertical strips. One of these vertical strips is there. For example, kth vertical strip is there. What the height or that distance or the difference between them is going to be delta xk, for example. So if you rotate this vertical strip around y-axis, it will turn out to be a circular object. Have a look. The outcome. It will turn out to be something like that. Something like that. I mean, the graph is not appropriate anyway. So it will turn out to be a circular object. Since it's a solid thing, there is no gap in between them. So we are talking about this whole thing. This is how it is known as disk. So what are the important components are there? One of the most important component is radius. So if you label the radius as r of x. So it's a circular object, but there is going to be a width of that one. The height of that one is a, and height is going to be delta xk for the kth vertical strip. So now it's a circle, but now since you are rotating this vertical strip about x-axis with that much height, you can say that much. So area is there for two-dimensional object, means circle is there, and on top of that one more dimension is there, the height is there. So once you combine the area of a circle with radius r together with one more dimension, it will take you to volume. So subdividing the region, subdividing the area into finally many vertical strips by taking one example of kth vertical strip, for example, the radius, eventually it is going to be radius r of x. Once you rotate this one about x-axis, so it will turn out to be three-dimensional object. Two-dimensional object is the area described in the plane xy plane, but with this rotation, it is going to be three-dimensional object. So since with this rotation, it is going to be circular object, we combine area of circle together with one more dimension, it is going to be volume. So volume of one disk would be, so merely behind the scene, what is area? Length into width into height. So for example, if you take into these two components to be described by pi r of x square, I mean length into width area, and for that circular object it's pi r square, then together with delta xk, it is going to be volume. Third dimension, height is going to be mentioned together with the two-dimensional object, and the area of two-dimensional object, length into width, means pi r square together with one more dimension, delta xk, it will take you to volume, length into width, and now with one more dimension, height. So look into the description now. We have got this one. So what we do? Suppose the region, I mean the area bounded by y is equal to f of x over the interval from a to b is subdivided into n vertical strips. A disk whose radius yk or r of x and height delta xk, the volume would be pi radius k times third dimension height. So volume of one disk is going to be this one. Sum of volumes of all n disks. Bring this mission sign over there. So if there are infinite number of disks, then the sum of volumes of n disks is going to be described by this one. And again, you need to bring in the concept of Riemann sum. On top of that, the limiting value, it will take you to definite integral. So this is all. The formula is there. The very first formula is there. V is going to be captured by looking into this definite integral pi r of xk. What is r of x? It's basically y. What is y? Y is also described as f of x. So many ways you can look into this formula. So pi y square dx over the interval from a to b. So this is the first formula. Second formula, you can look into that yourself. I mean, if you look into the graph along the line y-axis, just like we have discussed in the last lecture, the second one, you can do it yourself. The volume of the solid generated by revolving y-axis, the region between y-axis and the graph now x as a function of y over the interval from c to d is given by this formula. So v is equal to pi x square. What is x? Is a function of y, and merely it is going to be radius r, capital R. So all you need to integrate this expression pi x square or pi f of y square, because x will be given as a function of y. So these are the formulas to be taken into consideration for disk method. Disk means solid thing, there is no gap. So here you go with few examples from the exercise. So I believe that it will be exercise number 6.2. Okay, 6.1. Yep, here you go. 6.1. Find the volume of the solid generated by revolving the shaded region about the given axis. For example, the shaded region is A, and you need to rotate it about x-axis. About x-axis means you have to describe y as a function of x. So get y as a function of x, it will be 2 minus x divided by 2. So your expression would be like this one. So this is going to be the radius. Now what is radius? It's basically the portion of the curve, and the curve is there, means in this case is a special case like a straight line. So since it is going to be striking the walls of the straight line, so at this point in time it will be described by y is equal to 2 minus x upon 2 for a specific value of x. In general, it is going to be 2 minus x upon 2, y is equal to this one. So this is basically radius. By default, it is going to be y. So formula is there, pi y square over the interval from 0 to 2. So this is all you need to look into the integral. 16, you need to rotate it about y-axis. Now this is going to be the radius of the corresponding vertical strip. In this case, it's a horizontal, but if you look into the baseline as y-axis, so again, it is going to be vertical one. X is a function of y, already given to you. X is a function of y. Y as a function of x over the interval from 0 to pi by 2. Further, you can try a few more examples. Y is a function of x. Y is a function of x. Y is a function of x. And the limits are there. So this is how you can try these examples up to 24 by using disk method. Once you make a rotation either about x-axis or y-axis for this particular solid, so it will take you to disk, because we have to make a difference between disk and washer. Washer is going to be a different formula. Formula is there to find the volume of solid generated by revolving about x-axis, the region bounded by two curves now. Curve number 1, y1 is equal to f1x, y2 is equal to f2x over the interval from A to B is going to be this one. So difference is there between volume modeled by disk or volume modeled by washer. Now we are going to talk about washer. So same idea is there. We will subdivide the interval from A to B into finally many pieces, and once you rotate it, it will eventually take you to the idea of washer. Have a look. the geometry of this concept. In the meanwhile, I take your times. Okay. Yeah. So no, we got an idea about this. This means solid thing. For example, if you cut it down in the form of circle, cut a circle from here. Now that circle is a complete region, two-dimensional object, but because of this third dimension, like this one, the height is there, that dimension. Third dimension would be involved together with circle. So this is how we talk about the volume, and that is going to be the height. Keep an eye on this formula. We look into the other way around, the Gaussian method now. What we have at our disposal in the x-y plane, we got two curves. The boundaries are there, x equal to a and x equal to b. So pretty much the same idea is there. What we do basically, we subdivide the region for this curve, for that curve, and pretty much the rotation is there. Again, the rotation is going to be made about x-axis. So what will happen? There will be finally many vertical strips corresponding to the outer curve. And for example, the outer curve is a y1 is equal to f1 of x. And if you label that, for example, in the article r of x, capital R, for example, that radius is going to be capital R. And for that one, for the lower curve, that one is basically y2 is equal to f2x. Two curves are there, the upper curve and the lower curve. So we are talking about this region to be rotated about x-axis. So the corresponding to the outer curve, we subdivide into finally many vertical strips. Against one vertical strip, there is going to be a circular object. The radius is going to be r of x. For the inner curve, the radius is going to be described by a small r of x, for example. Then what happened behind the scene? What happened? You see that it is going to be something like that. The gap is there, and that gap is there. I mean, the axis of rotation is going to be x-axis, but it is not going to be a part of the solid generated by revolving this region about x-axis. In the previous case, we see that the axis of rotation is also a part of the solid generated by revolving the shaded region. Now the shaded region is there, far away from the x-axis. X-axis is the axis of rotation, and we are going to rotate this region bounded by the upper curve, the lower curve, from the left by x equal to a, from the right by x equal to b. So this region is going to be rotated, just like, for example, the region is there. I mean, just the region in between these two fingers, and the axis is there, like the marker is there. So we are going to rotate this one about x-axis. What will happen? This axis of rotation will not be a part of the solid generated by revolving the region between these two fingers. So what it will turn out? It will turn out to be washer, like a washer. No, I mean, this is going to be the thing that we are talking about. So this is going to be the solid thing. So it's like two circles, two concentric circles are there, having the same center.
So the radius of the inner circle would be small rx, and the radius of the outer circle is capital R. So this is how we will be having two circles with a gap between them. You see that this is going to be a gap. There is nothing. Hole is there. It's a circle. Another circle is there. So the region between these two concentric circles will take us to the volume with the rotation. So we need to know the radius of the outer circle. We need to know the radius of the inner circle to get down with the formula. So what we see with the formula is there I A to B capital R. One of the form of the formula is there minus small r dx. So pi is taken outside the jacket. What is this? Outer radius squared. What is that? Small r. Inner radius squared. So if you look into the foundation of the disk method, pretty much on the same line. Now we have to consider two radii. The radius of the outer circle, radius of the inner circle, outer radius is corresponding to the upper curve, inner radius is corresponding to the lower curve, because we are talking about this region. And the region is there in two-dimensional space, but once you rotate this one about x-axis, it will turn out to be three-dimensional object. And the geometry of that rotation will take us to washer. And we know washer, the nut and bolts, and we utilize in our daily life. Washer is there, so gap is going to be there. So there is nothing in between them. So it's basically the region between two concentric circles with same center. We will be having inner circle, the outer circle, and that region is going to be considered. Eventually, it will take us to volume. So formula is there. We need to know outer radius squared, inner radius squared, take the difference between them, integrate it with respect to x over the interval from A to B. So this is all. The volume of the shaded region will be captured now by utilizing washer method. Now, as a conclusive remark, what is the difference between disk method and washer method? Where do we utilize two radii and where do we utilize only one radius? The key thing is that, take a note to that vital difference between them. When the axis of rotation is a part of the solid generated by revolving the region, we need to utilize disk method. And when the axis of rotation is not a part of solid generated by revolving the region about that axis, it is going to be washer method. So when axis of rotation is a part of the solid, there won't be any gap. It will be a solid thing. So eventually it will be a disk. And when axis of rotation is not a part of the solid, generated by revolving a certain region about that axis, it means that there will be a gap. And once there is a gap, geometry will take us to washer. And washer means we need to know two radii, radius of the outer curve corresponding to the outer curve and radius corresponding to the lower curve, and eventually it is going to be inner circle. And this is all. You make the difference between disk method and washer method.
The other possibility is pretty much on the same line. I mean, y1 is a function of x, y2 is another function of x. If x is a function of y, I mean, now you are considering y-axis, along y-axis, pretty much on the same line. You look into the graph and the outer radius, inner radius over there, you can do it yourself, pretty much on the same line. Now we go back to exercise by taking few examples. Azan is taking place. Sallallahu. So, all right. So take into these examples, although it is described over there, find the volumes of the solids generated by revolving the shaded regions about the indicated axis, for example, about x-axis. You see that shaded region is this one, the region between the upper curve is y is equal to 1, straight line, special case of the curve. The lower curve is going to be described by this one, that one, the blue curve is it. So this is the shaded region between the upper and the lower curve. So once you rotate this one about x-axis, you will see that this x-axis won't be part of the solid generated by revolving this region about x-axis. So you see that it will be like a washer. So only you need to bring the formula integral over the interval from minus pi by 2 to pi by 2. 1 square being the radius to the outer curve, corresponding to the outer curve, there will be outer circle. Minus square to this expression being the radius, inner radius corresponding to the lower curve. So it's a matter of integrating from minus pi by 2 to pi by 2. 1 square minus square of this one with respect to x. So this one has to be rotated about y-axis. So you will see that that is going to be from here to there. It will be the outer radius, x equal to 1, and the inner radius will be described by x is equal to tan of y, function of y. Outer radius minus inner radius, pi from the formula over the interval from 0 to pi by 4 along the line y-axis. You just imagine to make the concepts pretty clear. If you change the axis from y-axis to x-axis, and the rotation has to be made along x-axis, then you need to apply disk method, remember. Same example, 34. But if you change axis from y-axis to x-axis, then if you rotate this region, this shaded region about x-axis, axis of rotation, that one, will definitely be a part of the solid generated by revolving this region about x-axis. So then you need to apply disk method. Wherever you see the axis of rotation is a part of the solid generated by revolving the region, you need to apply disk method. Otherwise, it is going to be washer method. As you see again clearly, once you rotate this one about x-axis, disk method. Once you rotate that one about y-axis, this axis will be a part, disk method. About y-axis, yes, disk method. About x-axis, yes, it is going to be a disk method. Few more examples are there. You need to look into the plot appropriate graph is there. It is not going to be the exact graph. Rough sketch is there. Y is equal to x. It's a straight line. Y is equal to 1, x equal to 0. About x-axis. Look into the graph bounded by two straight lines. Y is equal to 1. So horizontal line is there. X equal to 0. I mean the vertical axis. And then y is equal to x, straight line inclined at an angle of 45, bisecting the first quadrant. So no, the region in between them. So it will be the upper portion of this curve under that straight line from the left hand side bounded by that straight line. So look into the rotation. So I guess over here it will be graph something like that, straight line is there, and that one is going to be the portion. And once you rotate it about x-axis, x-axis won't be part of the solid. So this is all you have to utilize washer method. There are further technical questions out there. I mean, the region in the first quadrant bounded above by the line, below by the curve, and on the left by the x. Yes, they are. I mean, you can handle these examples. So I would ask you people to look into those examples from 15 to all the way 44. For practice purposes, you need to look into those examples from 15 to 45. You got manual to this reference book, so it will be very handy to get an idea about the implementation of this method, about washer method. So at least you will get hint from there. From the manual, it's available online. You can figure out this one. Search on Google. And in this way, we are going to conclude this one. All right, so that's it for today's lecture and the end of semester.